Hey, hello everyone. Welcome to today's discussion of Biweekly Contest 173 of Leetcode. We will be discussing all the problems A, B, C, and D. So let's move forward to the first question. The question says that we are given a string S and an integer K. We want to reverse the first K characters of S and return the resulting string. Okay, so this can be solved using two different approaches. The first approach is writing a for loop for k by 2 length, that is up till the middle of k portion of the string, and reversing the corresponding letters. But this is a little time taking process. We already have a predefined function for this in C++stl, which is the reverse operator. So let's learn how to use this reverse operator. So this t dot begin is a iterator. Okay, let's say we have a string or an array which is like this. All right. So this first letter, the memory address of this first character, that's called the first iterator of this string, and this t dot begin represents that particular address. Until which address do we need to sort it, since we know that strings are present in our memory consecutively, so we just iterate them consecutively. So up till which length do we need to iterate? K lengths. This is the first length, this is second length, this is third length, this is fourth length, and similarly up till which length we need to reverse, we just write it as t dot begin plus k, and then we just reverse it and return the new string. This was it for the first question, and it was very simple if you just knew the predefined function which is available in C++. So let's move to the second problem now, which is minimum subarray length with distinct sum at least k. Okay, so we have a very famous problem on Leetcode, or you can find it on other platforms like CSES as well, which is a two pointer problem. You can just search it uh, on Google and you will find that problem. If you want, you can comment, and I will be providing you the link of that problem as well, where we want the minimum length of uh, a subarray which has sum greater than equal to k. So this problem is a variation of that particular problem. So it is very much recommended that you solve this problem, that problem, after watching this video or attempting this problem, because I will be explaining that problem as well. So that is recommended. So what does the problem say? You are given a integer array nums and an integer k. Return the minimum length of a subarray whose sum is sum of distinct values present in subarray is at least k. If no such subarray exists, return -1. Okay. So this distinct keyword is the variation of problem that we are being demanded upon. The original problem just say that we need to return the minimum length of subarray, which is sum at least k. So let's understand it. Let's understand the beginner problem, which is the original problem. Now, where we are given some numbers. Let's say we are given this array and this k, and we want to find out a array uh, which has sum greater than equal to 4, and it is a subarray of this nums array. Alright, and we want the minimum length of such a subarray. So the key idea here for solving this basic problem is, for each starting index, find the index, find the ending index. All right, what do this starting index and ending index mean? For example, we start with this 2 here. All right, if it's not visible, I'm writing it again. 2, 2, 3, 1. If we are starting from this 2 here, which particular index will give us sum greater than equal to 4. It is the second index. We start from first index and we end at second index. Starting from second index, what is the index that gives us sum greater than equal to 2? It is index 3. So because 2 plus 3 is equal to 5, which is greater than equal to 4. Now for this 3, what is the index? It is fourth index. Sum is 3 plus 1, 4, which is greater than equal to 4. Now for this one, no such index exists. So among all these starting index, the minimum possible ending index need to be found, and the length of that particular substring is a contender for minimum length of the string, which gives sum greater than equal to k. Okay. So one of the key observation here is for starting index I and j, if starting index of I is greater than starting index of starting index I is greater than starting index j, that is I is greater than j. For example, this 2 and this 3, the ending index of I will also be greater than ending index of j. All right, why so? Because if we say that this particular index gives a sum up till the next index, all right, then what is the scenario? Maybe this is a particular scenario where it gives the sum up till the next index. 2 plus 2 is 4, which is greater than equal to 4. Okay, now this 2 has some numbers lesser than the number that was reduced from initial subarray. Okay, so either this particular uh, leftover term is itself greater than equal to 4, or it requires some extra numbers. Here this should be greater than equal to sign. Okay, so if it requires extra number, then j needs to be increased, that is ending index increases. So uh, we just need to iterate over to the next possible index, which gives us sum greater than equal to 4. Okay, so this particular conclusion is easy to digest. If you do not digest it, like, you can just dry run over some test cases and watch the video again, which I just explained right now. Okay, so if for each starting index I, we find a ending index j, and since I and j both are in increasing order, all right, because same j can never go back, so we need not move our iterator to backward. So starting index iterator moves n times and ending index iterator moves n times. So overall, uh, we get a solution for the basic problem in O of n using 2-pointer. All right. But what is the variation here? The variation is that we should always have distinct values present in our subarray. For example, here this 2 and 2 do not give sum as 4. Only distinct values need to be taken over. So only 2 will be taken. So this particular subarray gives sum 2. Now if we take this number, then sum goes up to 2 plus 3, which is 5. Similarly, this subarray gives sum 5 because both of the numbers are distinct. Alright, now how can you solve this? Will the initial approach of 2-pointer work again? Yes, it should, because this monotonicity holds here as well. Because if starting index is greater, then ending index will also be greater than equal to. Alright, because of this very same reason. Because if uh, this string, let's say here we have some strings, gives some as let's say k. Now we are claiming that for a greater I, let's say I is here, we have a smaller j. here. Okay, so if this portion already gives sum greater than equal to k, then what is the need to add this portion into our initial uh, array or initial sub array? All right, that is what I wanted to say. So here also this particular condition holds, because if a number is distinct in this part, then it will also be distinct in this part. So there is no such condition where this particular sub portion will give extra sum, sum greater than okay, this sum, this portion gives sum greater than k in this sub array, while it gives sum greater than lesser than k in this sub array. It can never be possible, all right, because if some distinct number is here and it is not counted here, it must have been counted here or here, all right. So even if we remove the counting from here and start counting at this portion, then these both conditions are very much similar, all right. I will repeat it again in case you did not understand. I wanted to say that, let's say we had a number here which appeared first time, like there was a 2 which appeared here for the first time and it appears here for the second time. Now this subarray gives sum as 0, and let's say this is 2 and this is, okay, this is just a 2. Now this subarray in this starting index gives value 2 instead of 0 here. So there can be a possibility that a smaller ending index gives sum greater than equal to k in this part. But if we think it in different order, let's say we do not consider this 2 into our uh, answer, all right, we have cut over this 2 and start considering this 2 now. These two cases are similar. Okay, so if uh, the sum ends over at this portion, that is this j for this I, then it end over at this j also for this I, all right. So monotonicity over j is held in this variation. Also monotonicity of ending index is held, all right. It just means that for two starting index I and j, if j is greater than I, then ending index of j will be greater than greater than equal to ending index of I, all right. So let's move to the implementation now, because monotonicity helps. We can use just the 2 pointer again, and to keep a track of what are the numbers that we have already seen previously for this starting index, we can keep a map, and if we see that same number again, no need to add that into the sum. If we have seen that number for the first time, add it to the sum. So let's move to the implementation part. So that is why I wanted to say that you can see the implementation of that famous problem first, because it will be easier for you to digest this particular implementation afterwards. So here we have taken the in array itself and the sum k. Now first find the size of our inputted in integer vector. Now this j is the ending index up till starting index -1, that is no starting index have appeared so far. So ending index is also invalid, that is we keep it as -1. Now initial sum is 0. Answer represents the minimum length we have spotted so far. Now keep a map, as we discussed earlier. We can keep an ordered map as well, because an ordered map gives complexity O of 1 on average, and normal map gives complexity log n. But there are some hash collisions which you can study for interview purposes if you are interested. Rather, both of them have almost same functionalities, and unordered map is better in time complexity wise. Okay, so for this starting index, iterate over j until the sum is smaller than k. Okay, now add this number into our map. If it has been added for the first time, then its frequency will be 1. Now if frequency is 1, add it to the sum. Now keep following this particular step until one of these two conditions appear. First condition is sum increases more than k. Then we have got a range, we have got a j for this starting index. And if we have got up till n, that is we got no uh, ending index for this starting index, then also we stop. Then if we check if sum is greater than equal to k, if j is not n for sure, because we have got an ending index, then sum will be greater than equal to k. Then initialize our answer was the minimum length we have spotted so far as the initial answer comma minimum of initial answer comma the current length, which is j minus I plus 1. Now we need to remove the ith index because we are moving forward. For this starting index is over. Now next starting index. So next starting index do not contain the previous element, all right, into its range. So remove it from the map if uh, this value is equal to 0. That is, in this range no same value is present, then only it will be removed. Okay, it will be removed only when it's none of its frequency is present. If one of its frequency is present, all of them have same contribution, all right. So if none of them is present, then decrease that value from sum. Now at the end, check if answer is equal to int max, that is what we initialized earlier. Answer will be always smaller than int max, all right. Now if no answer is valid, in that case just print -1 as asked. If not, then return the required answer. That is what we have found so far. This was it for this problem. I would highly recommend that you solve the famous two-pointer problem first before implementing this problem. It would be very much easier to understand, grab, and digest this problem if you have solved that one. Okay, so let's move forward to the next problem now. So let's move forward to the next problem, which is find maximum value in a constrained sequence. You are given a integer n, a 2D integer array restriction, and an integer array diff of length n minus 1. Your task is to construct a sequence of length n denoted by a0 a1 up till a n minus 1 such that it satisfies the following condition. A0 is 0, all elements in sequence are non-negative. Okay, for each index I, uh, where I is from 0 to n minus 2, abstract value of, okay, absolute value of ai minus ai plus 1 is smaller than equal to difference, which just means that consecutive elements I and I plus 1 have absolute value uh, with a difference of diff I. Okay, for each restriction at I, index at I comma max val, the value of at position index in the sequence must not exceed max val. That is, a at I index is smaller than equal to max val. Your goal is to construct a valid sequence that maximizes the largest value within the sequence while satisfying all the above conditions. Okay, so first let's analyze the problem. What did the problem say? So we have a array where we know that the first element is 0. Now next elements are, let's say, a1, a2, a3, a4, and a n minus 1. Okay, let's say ax. Now there are some constraints. For some of the indices, let's say index 1, index 2, index x, we are said that it should be smaller than equal to 5, it should be smaller than equal to 4, or it should be smaller than equal to 3, which is not in our hand and it is given in input. All right. The second condition is we are given a difference array whose name is difference, not the data structure. So for consecutive indices, that is A2 minus A3, subtract them and take the absolute value. That absolute value should be smaller than equal to D2. Difference uh, array at 2. All right. So let's analyze this problem. How many constraints do we have? Two constraints. But one constraint is uh, the value should be uh, smaller than equal to D2 difference array, and the second constraint is restriction constraint. So, and what do we want? We want the maximum value possible. Okay, the maximum value should be maximized. The largest value should be maximized, and we need to return the largest possible value. So, let's move from left to right, and we try to maximize. Okay, so this problem is mostly constructive. So we just need to uh, construct a sequence. All right, so let's try some naive approaches. All right, that comes to our mind. Let's move from left to right, trying to maximize our largest value. All right, so for this test case, let's try to do this. All right, the first value is 0. There is restriction on third index and eighth index. Both of them should be smaller than equal to 1. Let's copy the difference array here. The second value, the difference between first and second value should be smaller than equal to zeroth value, and first value should be smaller than equal to, okay, so is it zeroth and first? The difference at 0 represent uh, that a at 0 minus a at 1 should be smaller than equal to a at 0. All right, so these two values should be smaller than equal to 2. All right, so and we want to maximize our largest value, so let's write it as 2. All right, there might be some edge cases here, but we are not considering that right now. We just want to maximize it. We will consider that later. Now again difference is 2 and the index is 0 1 2. All right, no restriction on that index. So how much can we increase it? By 2. All right, we already always want to increase our largest value. Now this is the third index. What does this difference array say? Difference array says that 4 plus 3 is 7. So this can go up till 7. What does restriction array say? Restriction array says that it can be up till 1 only. All right. So this can never be 7. So the most restrictive one should be followed. Okay, this says that this should be smaller than equal to 1, and this says that this should be smaller than equal to 7. So the most restrictive one is restriction array. So this should be equal to 1. All right, because this follows both the conditions. Now next we move forward. See, we can see that even now the difference is 3 only. All right, 4 minus 1, it is equal to 3. While there might be some conditions that this condition uh, is not followed. That is, if this was written as 0 and we had initialized this as 0, then we see that this 4 minus 0 is greater than equal to 3, greater than 3, which is not valid. Okay, our difference value should be smaller than equal to 3. So what about that condition? We will consider that later, but keep in mind that such conditions are arising in past. Now what is the next restriction? It is 1. What is the index? 1, 2, 3, 4. Fourth index. No restriction. We have a restriction on 8th index. So we will consider that at 8 index. 4. Okay. And 5th index, what is the restriction? 4. So it is 6. We want to maximize the value. At 6th index, it is 11 because 6 plus 5 is equal to 11. At 7th index, it is 12. At 8th index, it is 13. Alright, I am just adding the difference. Now we see that this 13 is much greater than the restriction 1 we had. Alright, so the restrictive one, most restrictive one will be followed. So it will be equal to 1. Now see that this difference is very large. It is 11 and we said that difference should be equal to 1. What to do now? Okay, first let's try to maximize the largest number. Then we will see about those restrictions. All right. So what is the next restriction? It is 2. Difference is 2. So value will be 3 because here it is 1. Now, there are some restriction. Let's say at index I, which restricts a index at j. And we know that j is smaller than I. Okay. So if we see from right to left, okay, only a index here restricts a index later on. All right. For index j, uh, it restricts, it causes a restriction on index which are present earlier than current index. Let's write it down. Now, after this construction, each index causes restriction on only the indices present before it. Okay, why so? Because while moving from left to right, we already managed that the left index and right index, they do not cause, the left one do not cause problem on right one. All right. Why so? Because we made sure that the difference between them is smaller than equal to diff. All right. Now, if this one is more restrictive, that is, this said that your range can be between here to here, but this one came out to a condition where it is smaller than that range. Okay, so this can never be changed now. Okay, this cannot be increased. Now, for a I greater than j, I cannot be changed to manage j because we have already tried it earlier. All right. Now we have only restrictions from right to left. So iterate. So to solve this, because only a j is having restriction due to a I which is greater than j. So move from right to left to mitigate these restrictions. Alright. How? Here these two have restriction of 2 which is followed. Very good. Now these two have restriction of 1. Alright. Now can this index be changed? No, it cannot be changed because this has a restriction due to restrictive array. The next, that extra array that we were given, we already tried to make it in range with this I. All right. Now this value cannot be changed to mitigate this because it is already max of what it could have been. All right. It cannot be increased any longer. Now to solve this, we need to decrease this value. How to decrease this? The restrictive value is 1. So this can be up to 2. All right. So that absolute value between these two is smaller than equal to 1. Now again, these two have been handled with 2. These two have been handled with 1. Now the next handling scenario is 1 again. So this can be up till 1. All right. Now the next value, it is 5. difference between these two is 5. Okay, very good. Now keep in mind that these values have already been changed due to values present before it in the very first process that we discussed. Now these cannot change due to improving the restriction of these values. So only these values need to be changed. All right. Now this 6 has been handled again. Now this 6 and 2, this has a difference of 4, and the restriction value is difference value is 4, which is very good. Now this 2 and 1, it has restriction value 1. Very good. 1 and 4, restriction value 3. Very good. Now this 4 and 2, restriction value 2. Very good. This 2 and 0, restriction value 2, which is very good. Now what is the maximum value present here? 6. Alright. And what is the answer? It is 6 again. Okay. So in this very construction, we initially made sure that each index I gets the maximum value possible, keeping in mind the values present before it. Alright. Now there is no restriction on this I that changes this I due to a I present before it. Okay, if this is already max of what it could have been. Now if there need to be there is need of some change, that change need to be done on values present before it. Okay, so iterate from right to left, because for the rightmost index there is no restriction present. All right, it cannot be changed any longer. So it is very much good to be said as final. Now if the previous index need to be changed due to the last index, then change it. After changing it, it is the final value of that particular index. It is not going to change any longer. Okay, this is what uh, conclusion we had earlier, and due to which we came to the final solution, which is iterating from left to right and then from right to left, keeping in mind the restrictions and following them. All right, so let's start with the implementation. We have a vector which we wanted to build, which we wanted to construct. Now keep a map for restrictive values so that we can make sure that what is the restrictive value at what index. So for this index, restrictive value is this. All right. Now move forward from first index up till n minus 1th index. Now the current index, what is the maximum value it can achieve? It is the previous value plus the difference value. Okay, we want to maximize it, but if there is a restriction, we need to make sure that the value is smaller than equal to restrictive value. If it is already smaller, very good. So we take min with the restrictive value. All right. Now there are some constraints from right to left that need to be mitigated. So mitigate them. Iterate from I minus 2 up till I minus 1. Why I minus 2? Because we are very much sure that with this construction, I minus 1 has its final value. Okay, it will not be changed any longer. It is the maximum of what it could have been, and it can never not be changed. All the constraints are satisfied for it. So if the constraint of difference is not satisfied for n minus 2 and n minus 1, n minus 2 is surely to be changed, n minus 1 is not going to be changed. Okay, so change n minus 2 if there is some such restriction, that is minimum of what value it could have been, that is if it is very much higher than the larger value, then restrict it with vec I plus 1, that is next value plus the difference value. Okay, at the end we want some the maximum array, not the array, it is a variable which stores the maximum value over the built vector, the constructed vector. Okay, so take it max with the I minus 1th value, then taking it, the max with I minus 2, I minus 1 up till first index, the maximum value which we get is to be returned. All right, this was it for the third problem. Now we are going to discuss the fourth problem. First, let's discuss the time complexity of this. Here we have a ordered map which will take O of log n for operations of adding, accessing, and deleting an element. All right. We can reduce the complexity by using unordered map, but it works on lead code. It do not work on code forces. So we will be using ordered map only in our discussions, and iterating over the size of restriction array, which is smaller than equal to n. Okay, so it is O of n log n here, this loop. This loop again is O of n log n, finding an element and accessing it, which is log n. Now, this again is n log n because we are iterating from n to 1, and we're not accessing any map value. Okay, so it is O of n. So maximum of these three, which is n log n, that is the time complexity of our code. So let's move to the fourth problem now, which is count routes to climb a rectangular grid. So the problem says you are given a string grid of size n, string array of size n, which is named grid, where each string grid I, that is each character in grid. Okay, each string in grid has length m. The character grid is one of the following symbols. This is the representation of grid. Each grid contains some rows. The length of each row is constant, which is m. Here it is 2. And the elements are either dot or hash. Dot represents that cell is available, and hash represents the cell is blocked. You want to count the number of different routes to climb grid. Each route must start from any cell in the bottom row and end up in the top row. Okay, so there is a grid. We have some rows. Okay, and we want to climb from the lowest row to the highest row, such that there are some available cells and there are some blocked cells. Or okay, this is the part of question discussed so far. However, there are some constraints on the route. You can only move from one available cell to another available cell. Okay, that is available is dot. You can move from one dot cell to another dot cell. The Euclidean distance of each move is at most d. Okay, so if we move from this cell to this cell, the Euclidean distance between these two should be smaller than equal to d, and both of them must be available. What is Euclidean distance? What we learned in mathematics, which is uh, root of square of difference of x-axis plus y-axis. All right. Each move either stays on the same row or move to the row directly above. This means that if we are in row I, then we can either choose to stay on the same row such that all these two conditions discussed earlier are valid, or we can move to a row above it. We cannot move to row very much above it, that is 2 rows above it or 3 rows above it. We can move just directly above. You cannot stay on the same row for two consecutive turns. That is, if we chose to stay on this particular row in some move, that is, we are at row I and we chose to remain at row I on some move, then on next move, surely we must move upward. All right. If you stay on the same row in a move, your next move must go to row above. And this move is not the last move. Okay. Okay. This is it. And you cannot, you have to make a move, okay, to another available cell. You cannot remain on the same cell. Even if you chose to move, remain on the same row. Okay. You need to move on some other column. This is it. If you have solved similar problems, it is very easy to crack it that this is a DP problem because all these similar problems are solved using DP. And since we want the answer modulo 1e9 plus 7, this is also a very much deciding factor that helps us decide that answer is solution is a DP problem. All right. So the question is a DP problem, and we want some DP state. All right. Very first thing which we think in DP. What is the naivest state you can think? DP at ij means the number of ways to reach cell ij. Naivest idea anyone could get. All right. Now let's try to visualize this state. Is this state correct? How to write the recurrence relations and so on. All right. So we have one of the test cases. This is better if we analyze this test case. Okay. What is it? Dot dot followed by hash dot. All right. Dot dot followed by hash dot. I'm writing it like this. And D is 2. Okay. So first thing, if we want to move on the same row, then D will be 2. So for cell ij, we can move up till I minus 2j. Okay, sorry, we are changing the row itself. We need to change the column. Okay, 2 I comma j plus 2. Okay, in same cell. Okay, in same row. In another row, we should choose a value such that the difference of x-axis, which is 1, plus difference of y-axis square and root of this is smaller than equal to 2. All right. If we write it in little different form, it is equal to 1 plus y square is smaller than equal to 2 square. We took the root to other side of equal sign, less than equal to sign. Okay, which is equal to y square is less than equal to 4 minus 1. All right. Y square is smaller than equal to 3. And what is the root of 3? It is about 1.732. All right. Okay. So, and can we move in decimal? All right, we cannot. So we take the floor of this value. Okay. So for changing the row, what is the restriction on change in column? It is 1. Okay. That is, we can move from this cell to one cell to the left or one cell to the right. This one we could have, we could move. If there was a cell here, we could move at this cell. If there was a cell after this one, we could not move to this cell. Okay, because a change in y is smaller than equal to 1.732, and here change in y would be 2. All right, but we are given only one cell here in upper row, so this is it. So what are the possible roots that are given? The first root is 1 2. Okay, let's write down all the 4 possible roots that is given in our answer. There is a has 1 2. All right, this is the possible scenario. With this, keep in mind that we are analyzing the scenario which we will use in recurrence relation. Okay, the second case could have been 1 2 dot and has 1. Okay, we started from here, we moved here in the second attempt, and we remained. What is the third scenario? The third scenario is we could have started here, we could have moved here and then moved here. Okay, because in the second step we could choose to remain in same row but different column. Okay, so in third step we moved here. And another scenario, which is we started from here, we moved here, then we decided to move here. All right, these are the all 4 cases that are possible. Okay. And what was our DP state? And the answer is 4. All right. These are the 4 ways with which we can reach. What was the DP state we decided earlier? DP at ij represents the ways to reach cell ij using uh, this approach. Okay. And we move from bottom to up. So it is very much obvious that we would write a recurrence which is processing the lower rows first. All right. For the bottommost row, that is the starting row. Let's say this is the scenario. This is the scenario. Okay, only one rows, which is very much similar to uh, applying operation on one row. That is the bottommost row in all the other cases. All right. This is a dot. So one, that is the starting index, could have been here. One is here. A dot is here, so one could have been here. Okay, so these two cells are possible contenders of starting cells. Okay, so what is dp at ij for these two cells? It is equal to 1 because there is one way to start from here. This is our base case. Now in the second step, after starting, they could have moved to the same row, different column. Okay, so this one could move to this particular cell. So there could be a condition like 1 2. All right, we started from here, moved to here. So dp gets add upon by 1. Okay, this one also gets add upon by 1, and this one also gets add upon by 1. Okay, and what are the number of possible ways to move? 4. The sum of dp values at the end, okay, of the topmost row. This is it. So what did we discover about base case with this? For the bottommost row, if grid ij equals to dot, then it is a contender for starting cell. So dp at ij for this cell is equal to 1. Now after we have started from that particular cell, there is a case where for d rows backward, okay, d cells backward in column and d cells forward in column, we can move from these all cells to the current cell for remaining in the same cell, same row. All right, dp at ij is equal to sum over previous dp. Okay, the number of ways to reach that cell. dp at I, row remains same, j minus d to j minus d up till j minus x, let's say. Okay, where x varies from my d to minus d. Okay, all right, we move d cells backward, and at the end we move d cells forward. This is it. So can this be done using some data structure? Yes, prefix sum. All right, because these cells are consecutive, so we can build a prefix sum over the same row. This can be done in O of n using prefix sum. Okay, if we try to write it using prefix sum, what will we write? We will write is prefix sum at I j plus d minus prefix sum at I, same row, j minus d. We moved to j minus d. Is it correct now? No, we need to subtract one more cell. Okay, because we need to include j minus dth cell. Okay, so we subtract one more so that we can include that cell. Okay, and this was our base case to be certain. Now another case is case of moving one row up. Okay, so for that we calculated uh, like this. Okay, let's say this uh, 2 was actually the d here. All right, so if we write it like this, then at the end we can say that y was less than equal to root of d square minus 1. All right, which can be calculated in O of 1. All right, because this root operator, I guess it works in log n or O of 1. I don't really know it. You can search on Google, but most probably it works on log n. All right, so find the root using this built-in sqrtl function. Okay, sqrtl. L is for long because this is integer. You can use sqrt as well. So, and take a floor of it. This is our y. Okay, now do the same thing. That is dp of, because we already have prefix sum and we want the values of lower row from y cell backward up till y cell forward. Okay, so we move one cell, one row bottom and j minus y. Okay, j plus y minus one row bottom, j minus y. We need to include this particular cell j minus y, so minus 1 extra. All right, and this is the uh, recurrence for moving one cell upward. All right, just as we discussed in this part. So these are the all possible recurrences. Apart from this, no recurrence is possible. Okay, so base case is starting from the bottommost cell. After that, we apply the operation of moving in the same row. Okay, which is applied using this recurrence. All right, now we move one cell upward because we cannot remain in same row for two times. All right, so for this recurrence will be held. Now if we are on this row, we can again for the first time we can again move to the same row, so apply this recurrence again. And after this we have remained in this row and we have come to this row, so both those conditions are over. We cannot remain in this row any longer, so move one row above and process that row. Like this, keep processing all the rows until we reach to the topmost row. Now we, for each cells, we have the number of ways to reach that particular cell. Keep in mind that these dps are applied only to those cells that have dash dot available. Okay, that cells are available. If those cells are blocked, no particular operation will be applied. Okay, so dp of ij will be 0 for that particular scenario. Now this is it. For the topmost row, calculate the sum of dp values in that particular row, and that will be our answer. The major part in this problem is of implementation. Okay, and we have written the recurrence relations, all the possible recurrence relations. Now we just need to see this in form of implementation, because writing prefix sum is little lengthy, because we need to make sure that this particular value do not go in negative. If it goes in negative, what to do? If it does not, what to do? So all these cases need to be handled. Let's understand the implementation part now. So this is it. We want the answer modded with 1e9 plus 7. So we have constant value m. We built a prefix. So instead of using a prefix sum of n cross m, we use it with We keep calculating it every time using a prefix sum of length m. All right. So that is it. We start with base case, which was if the last row contains a dot, then dp value is 1. Now moving in the same cell, which is uh, first calculating the prefix sum. All right. If the current value is 0, then the current value is the prefix value. Okay, so for first index of prefix sum, that same value is repeated. All right. And for upcoming values, the previous value plus the current value. That is it. Here prefix sum taking modulo with m. Now the recurrence relation of moving in the same cell. If grid is not dot, that is this grid is not available, this cell is not available, then just continue, okay, because dp at that cell should be equal to 0. Now what is the minimum possible column which corresponds to this column in current operation? It is equal to I minus d minus 1. Okay, here we discussed it, j minus d minus 1. And what is the maximum possible? It is I plus d. Okay. And if it goes out of the range, just take min with m minus 1. Okay. Because it is the maximum possible column. Similarly, with minimum possible column, take it as minus 1. If it is minus 1, no need to consider prefix value because we want the overall sum. All right. And if it is not minus 1, if it is 0, then we need to remove that cell. So we need to take prefix sum. Similarly, what is this extra value? Okay, we cannot remain on the same cell. All right. So we need to remove the case in which we traveled to the same cell, which is equal to dp at the current particular cell, which is dp at n minus 1 I. Now if j1 is equal to 0, that is the left restrictive cell, left constraining cell is valid, it is greater than equal to 0, then prefix at j2 minus prefix at j1 as discussed here. J plus d minus j minus d minus 1. If it is not, that is j1 is not valid, it is a negative value. How to reduce a negative value? We cannot. So prefix at some invalid value is equal to 0. So no need to subtract 0 from here. Now we just need to remove the extra case we just counted and just modulo operations. Keeping in mind that if we subtract a negative value, okay, if we subtract a value from our dp, then maybe our modded value gets to negative. All right. So better keep it positive. So add m here and then take modulo with m again. Now again, build the prefix sum. After every operation, we need to build a prefix sum. All right. Which is same as what we built earlier. Now for all the cells. First, we find the y value, which we discussed, which I have named here as limit. The limiting value for bottom row. All right. Which is equal to floor of sqrt of d into d square minus 1. All right. We have calculated it as limit. Now, for each row from n minus 2 up till 0, what do we need to do? First, bring the control from bottom row to this row. What is the way to do this? Instead of using d, which we used here, just use limit value. All right. Same thing. We are doing this very much same thing. Just at that part. Okay. What is the difference between these two recurrences? Here we have d and here we have y. Though both the values are same. Similarly, in these two recurrences, here we have d and here we have limit. Rather, both the recurrences are very much same. Now, after this thing, we need to build the prefix again. Prefix is required every time. Okay. So build the prefix after applying every operation. Now again, the part of staying in the same cell, which is very much same as we discussed earlier. Here we had our row as fixed, which was n minus 1. And here we are varying our row as I. Alright. And keeping our column as j. Rest, it is very much Not very much same, exactly same. Now again, after this, build the prefix sum again. At the end, just return the prefix sum at m minus 1, which is equal to the sum of values at the bottom topmost row, all right, which is what we wanted to return. That is it. And this passes all the test cases. What is the time complexity of this code? We have just built a DP array of size n cross m, and taking modulo with m. Okay, so this particular loop is a O of m. This particular loop is a O of m loop. Then here also O of m loop. Here also O of m loop. Now this loop goes uh, for n times, and inside it there are some functions, some for loops which are going m times. So overall complexity will be n cross m. Here this loop also n cross m, this loop also n cross m, and this loop also n cross m. So overall time complexity, what is it? O of n cross m, which is very much computable, all right, because 750 into 750 is computable. That is it. That was the discussion for today. So we will meet tomorrow again for weekly contest. All the best. Try to do all the problems. Give your best. Thank you.